So I'm going to be talking about automated processing and visualization of multispectral image stacks today. Uh, some of this has already been talked about before, particularly different kinds of visualization that people are doing with multispectral image stacks. I'm going to be talking about some of the things that we're doing here at Duke with different kinds of visualizations, visualizations that we're looking at doing in the future as well, and also how we're trying to automate things as much as possible. Also these slides for this are available here at the URL at the bottom if people want to follow along if my internet connection becomes spotty in some way, or if you just want to be able to get the slides immediately after, or if there's something you have a question about. If I go past a slide, you can view the slides there. So what am I talking about when I'm talking about different kinds of multispectral image stack processing and visualization and automating the processing and visualization? So the goals for automating are really just accuracy, reproducibility, automation and efficiency, and also the main thing really is data or object insight. So we want to facilitate having actual insight into the things that we're imaging, not just pretty pictures. Pretty pictures are always nice, but ideally we're getting insight into the objects that we're imaging. So part of that is also ensuring that we have accuracy and reproducibility, that we're getting real knowledge about the objects that we're imaging, not inaccurate knowledge. So part of that is with calibration, like flat fielding, to remove the effects of sensor dust and non-uniform illumination during the multispectral imaging process. And then we also include calibrated color targets and rulers in the scene so that we can know physical dimensions and calibrate color to real color values that aren't just arbitrary color values. And the idea with automation is to make all of this possible at scale, to reduce the potential for user error and reduce the need to keep all derivatives forever. Because if you can automate the processing end to end, then what's really important is that the automation process is preserved, like the way that you process those images is preserved, and the original images are preserved. So that way, the particular derivatives that you generate, you can generate a huge number of derivatives for any given MSI session, but not needing to keep those around forever might be useful in some cases. And if you automate everything, then that becomes possible because you're not spending, however many hours hands-on doing the processing yourself that you're going to then throw away if you remove some derivatives. So if you automate that, then you can just run it again as needed. So data objects insight, we want to learn something about the objects of image. So for that, we need accurate images for individual wavelengths, but we can also see things on individual wavelengths that we might not see in a color image. So for example, obviously UV or infrared, individual wavelengths there, just that image without any advanced visualization or use of the entire stack, just a single wavelength image can give you insight into the object. But also reconstructed color images or pseudo color images. So reconstructed natural light images from a multispectral image stack can also give you information about the object. And then other visualizations like PCA, which has been talked about before, and any other 2D image visualization of our so-called 3D multispectral image stack. I'll talk about that a little bit later when I'm talking about when I'm saying multispectral image stack is 3D. It's just a way to consider the multispectral images. So here's an example of the processing and visualization pipeline for a multispectral imaging session. You start off over here with your flat fields, and you're seeing your objects that you're imaging processed in Capture One into TIFFs, and then clean the flat fields, apply the flat fields, and then you get to a flattened image over here, which those flattened images are now calibrated enough that you can use those for further visualization and processing. So in image J, you can generate a RGB image, natural light image, or RGB pseudocolor images, or you can generate PCAs. And then also from those flattened images here at Duke, we use a custom process here to generate other variations and visualizations of the image stack. And that's a process I'll discuss in a little bit. So the first part of that process, flat fielding, that happens before all the visualization, has mostly been automated at this point. Automated flat fielding thanks to Mike Toth and Bill have been automated as part of the Spectral XV shooting process. So you can automatically have the flat fields cleaned and applied during the shooting process. But here at Duke, we also had a large number of older images that needed to be processed or reprocessed from the raw originals. So we needed the flat fielding process that was automatic for that. So we developed some scripting for ImageJ to automatically take an image session, determine which set was the flats, clean them, and apply them to the rest of the images in that session without any manual interaction, so that we could automatically reprocess the large number of imaging sessions that we needed to reprocess for flat fielding. So the dream from there is not just flat fielding, but everything in that earlier diagram we want to automate, so that you just shoot your images and the computer automatically generates a standard set of all of the downstream derivatives and process data and visualizations without user intervention. And there is no step 3. So the idea is not just get to this flattened stage automatically, but also get to the RGB stage, generate an accurate color image from your multispectral image stack, and also generate your PCAs automatically, generate other variations, other visualizations automatically using any other custom process, just having to shoot the flats and your scene, and then automatically go through this entire process without hands-on user intervention. Of course, this doesn't preclude user intervention if you want to go in and do some manual reprocessing of something that interests you in the object later. This is just to automatically generate a stock set of visualizations, derivatives, and color image from any multispectral image session, so that you're not having to spend a lot of technician time building those images where that time can be used for something else. So what are the barriers to automated MSI processing? So one of the things is that we want to be able to automatically recognize rulers and color targets in images. So the color targets will give you information for accurate color reconstruction because they have known color values that you can calibrate to like a lab color space or RGB color space. And the rulers will give you physical image resolution. So the physical pixels per inch that you've imaged. And both rulers and color targets may need to be cropped out before generating certain visualizations in order to reduce their potential impact on the dynamic range available for generating the visualization. So what do I mean by dynamic range? Once you're outputting an image from values calculated from that whole multispectral image stack, you need to map all of those values into an 8-bit or 16-bit image. So you need to map the highest value in your data to the highest value available to you in the output. If you have a color checker in your output, that will probably always be at the maximum of that value range. So you're going to kind of wash out the available range to you if your object isn't also at the very highest values of that range that the color checker is in. So it's going to reduce the range available to the data that you're actually interested in, which is the object. So that enables you to see contrast there if you're able to crop that out. And rulers can also contribute to this if there's like a spectral reflectance or kind of sparkling if it's a metallic ruler. So those can include values at the extremes of the range that you're trying to map into for your visualization. Sorry, I got a cough a little bit. So we want to also automatically register the images for slight shifts caused by filter wheel light refraction or any other kind of registration difference that might happen between shots. And we also want to hook everything together end to end so that all this can be done automatically. So the current status of automated processing here at Duke, at least, is that we do have automatic flat fielding, we do have automatic ruler and color check detection, we have automatic image registration, we have automatic visualizations, but we just haven't hooked everything together end to end. So for automatic ruler and color check detection, this is an example of what our system does currently. This is a machine learning model that has been trained on, I think, about 70 images, which I manually labeled the ruler, color checker, and white point in. And all of the images that it's showing now, where it's highlighting that, are images that were never seen during training. So you can see for each image, it's highlighting the ruler, the color checker, and the white point. So that way, with those three things, we can both use the white point for reconstructing color images. We can crop out the color checker and the ruler from visualizations. And potentially with some more work, we could use the ruler detection to automatically set the physical resolution of the image. And so this is a slide that's actually from my colleague here at Duke in papyrology, Josh Sosin. And this is a piece of papyrus where you can see there's a section where it's completely unreadable in natural light, and with multispectral imaging, you can read the text. So that's the real goal with visualization, is to understand something about the object that you wouldn't be able to understand otherwise. And so this is an example of PCA, which has been talked about before. So this is a Pliny manuscript here at Duke that has a ownership illumination that is faded and difficult to determine with natural light. So with PCA, we can see what the actual cartouche looks like. It's like two lions on top of a castle. And from there, we can start to determine what the ownership of this manuscript was. And this is, I think, what, 16th century or so? So that's PCA, which has already been discussed before, as one example of a visualization that we'd like to be able to generate automatically without user intervention. For the more customized visualization that I'm going to talk about here, I'm going to go into some background on what we're actually trying to look at, and some of this might not be too necessary for this audience, but basically what we're dealing with multispectral imaging is we're not just dealing with this visible light spectrum. We're not just dealing with like a few slices of the visible light spectrum like we would with a normal color image. We're actually dealing with the ultraviolet spectrum, the visible light spectrum, and more samples on it, as well as the infrared section of the light spectrum. So to get to our sensed image, we have light that's projected onto the object, which it then reflects according to some intrinsic value of the object that we're imaging. So you can see different kinds of objects will reflect sorry, I apologize, differently across the spectrum. And that will be attenuated by our optics differently. So the filter wheel will come into play here if you're using it. Any kind of filter that's on the sensor will come into play here. Then the sensor sensitivity will also come into play. And flat fielding will correct for most of these non-uniform response curves at this point. So you're trying to get to the actual object's reflectance values here. And then this is just an example of multispectral imaging session, sped up considerably. And then some example multispectral image curves. So the light coming from the panels is not perfectly monochromatic. It's centered around a point. And that kind of comes into play with some of the color reconstruction stuff that I'm going to talk about. But it's important to realize that, you know, it is a curve. It's not perfectly monochromatic. It's not just at this one single wavelength. There is a slight distribution around that wavelength. So for the visualizations that we're generating here at Duke, we're taking this image stack that we get from the multispectral camera and then placing the images in wavelength order to generate a 3D image stack. And then by going through each pixel of that 3D image stack, we have a spectral response curve for each pixel. So that's a 2D spectral response curve. If we're trying to generate a 2D image that we're trying to visualize from that, we need to collapse that spectral response curve into a single value. So for example, if we're making an 8-bit image, we need to collapse that down to some values between 0 and 256. So we have to find some function to collapse this spectral response curve or reflectance curve into a value that we can see in the image. So the way we've done that is we've adapted some software that's actually used more typically for CT and micro CT visualization, so volumetric visualization. And by considering these images as a 3D image stack, as a volume that we can then use with the CT software, we're projecting through for each pixel and getting this response curve and then taking a value of that response curve. So for example, this is taking the minimum of that response curve at each pixel. So for cases where it's black, it'll stay black because that's the minimum value at that pixel. For the response curve, this is summing, and this is skewness. So this is actually fitting a line to this response curve and then trying to determine what the skew value of it is. And you can also do things like fit a line to it and determine the slope of the curve. Sorry. So these top images here are just grayscale images generated by calculating those values for each pixel. And the bottom images here are just those values remapped through a color map before generating the final image to try to give more perceptual contrast. Because the values that you can get from this can be highly variable, and with a grayscale image, it might be more difficult to see. So here's an example of using that with a 11th century manuscript of the Iliad. So this project was mostly concerned with trying to see the marginalia, the interlinear notes, a lot of which are faded. But on this, a lot of this marginalia down here is pretty readable, but all of it actually looks like it's pretty much the same ink in visible light. But with the multispectral visualization, what we can see is that we're getting quite different values for extremely close together ink here. So if we zoom in on that area, you can actually see what's going on. And this is a visualization of the slope of a line fit to the spectral curve for each pixel. So these two inks have very different slopes, even though they're for the same marginalia. And what we were able to determine was that this is the same ink that's used for an ownership inscription that's from about the 16th century at the front of the manuscript. So what it seems like happened here is that the ink was already fading after 500 years and was retraced partially. So these letter forms aren't all completely retraced. Some of them are partially retraced. Some of them are fully retraced. But it was already fading within 500 years of the manuscript's production. So had they not been retraced, it's not entirely clear if we would have clear readable marginalia for some of this. So what's the future work for visualization and automated processing? Well, obviously one thing is to hook everything together, but the other things that we're looking at here at Duke are more advanced dimensionality reduction algorithms for visualizing that 3D image stack, and also doing or attempting to do highly color accurate reconstructed visible light images from multispectral image stacks. So what I'm talking about with dimensionality reduction visualization is that we currently reduce dimensionality by projecting through the stack in wavelength order for each pixel. Sorry. But we could also use other dimensionality reduction algorithms with that 3D stack, such as UMAP, which is an acronym which is expanded here, or TSNE, which is another acronym expanded here. And the reason why we're looking at these two is because these are dimensionality reduction algorithms that have proven extremely useful and versatile in other domains. And they can also do things like clustering and outlier detection, which we could then visualize. And the other advantage of these is that they don't require manual intervention and manual labeling of data, so you can apply them automatically. So for highly accurate color, what I'm talking about is using the multispectral images to generate more accurate color than we're currently generating. Sorry, and then also generate more accurate color that you can generate with a traditional RGB camera. So with a traditional RGB camera, you have your scene, you have your camera sensor with a Bayer filter, which is actually physically bonded to the sensor, which filters out blue, green, and red onto each sensor bin. So then your raw camera file looks like this. So you have filtered colors for each pixel, which you then have to recombine into a color image. So you're losing sorry, you're losing color resolution in your final reconstructed image from that raw image. So with a monochromatic multispectral camera, you have more chromatic resolution because you're not filtering out with a Bayer filter at the sensor. So currently you can generate a color image by combining 3 RGB images from the multispectral camera and then doing color calibration. But ideally we could use the full stack of images to reconstruct directly into any color space and then project into other color spaces and calibrate. So for example, we could do CIE XYZ color space reconstruction, which is a color space which is larger than the RGB color space, but by using all of the multispectral wavelengths instead of just 3 selected wavelengths that are closely correspondent to RGB, we could reconstruct directly into this color space and then project in from there into any of these RGB color spaces and calibrate. So to sum up, automated MSI processing, kind of what the status and dreams are. We do have automatic flat fielding. We have automatic ruler and color check detection. We have automatic image registration. We have automatic visualizations. We still need to hook everything together end to end, and we'd still like to do more advanced visualizations and more advanced color reconstruction. So I'd be happy to take any questions.